for the midterm.
Good. Okay. So we've been, Professor Knopf, Eric, Mansouk, and I have been emailing back and forth, talking. It now has impressed itself on us that the spring semester goes by lightning fast. We'll have, of course, spring break coming up the last week of March, and as it should be, the second half. Once you have the basics down, the second half of this course, we can really appreciate now some very high-level external speakers coming in. So there'll be the balance will be lesser of these kind of technical talks. In fact, we just discovered, in fact, the calendar is rather full. So I'm going to try to hustle to get in a few more topics rather briefly. And then the rest of the time will be, of course, involved in these both sort of the capstone, project team discussions. There'll be a crisis simulation. There'll be an exam. We'll have external speakers. So there's not going to be a lot of room for more of these kind of formal technical lectures. So we're going to try to get things wrapped up. Today, if I'm lucky, I'm going to try to cover very superficially 3 topics. I want to, and I'm going to go a little bit out of order. I want to finish up separation technologies. I think we've decided that one of the things that needed to get jettisoned, unless we're lucky in some way and find some free time, is a discussion on plutonium reprocessing, which is, of course, hugely important from a proliferation point of view, but it's a rather arcane topic, and unless you're a junkie on chemistry, I'm neither a junkie nor have any expertise in it. It's something that may not have a lot of great value to go into a lot of depth here. So I'm going to finish up on separation technologies for uranium. Then I'm going to go one step ahead and talk very briefly about the testing program, a little bit about the history of the U.S. program, sort of milestones and agreements that we made, which impose restrictions on nuclear testing, underground nuclear testing, why we test, and then what is the modern paradigm after 1992, when the U.S. and Russia decided we actually now have a de facto moratorium on testing. The U.S. has not tested since 1992. What is this paradigm called the Science-Based Stockpile Stewardship Program, which is what supports the laboratories right now. Then I'm going to hop back, and with the remaining time, I will try to get started on a little bit about nuclear weapons defense. So back to enrichment, what we said was that we have this very small mass difference. It's sort of like 1 part in 100, sort of 3 parts, or 1 part in 80, sort of 3 parts out of 240 roughly. Very tiny mass difference between 235 and 238. 235 is a very rare species. It's the fissionable species used in weapons. What it allows you to get a handle and to separate 235 and 238. And quite obviously, you need the handle for you is some physics that depends on mass. A lot of physics phenomena depends on mass. We talked about electromagnetic separation, where for a given constant energy, 235 and 238 for compounds with 235 and 238 and have a small difference in mass, actually have slightly different momenta for the same energy, and therefore will have slightly different radii of curvature in the magnetic field. The other is, of course, diffusion, the phenomenon of diffusion barriers. That depends on mass. And again, you see how in this crash program of World War II, everything was stood on its head to get the job done. And now per diffusion stage, you get like a 1 part in 1,000 differentiation. And cascade that differentiation enough, and at great cost, with great advances in technology, you can go from a fraction of a percent uranium-235 to a effectively close to 100%. And again, at great cost and great scale. The third of the four I want to talk about is the gas centrifuge. This one is hugely important because I'm going to put up an article by Scott Kemp, a very brilliant young faculty member at MIT who spans bridges between technology and policy. He's a real leading light. Even at a very young age, he played a very central role as an advisor to the Iran nuclear deal some years ago. And much of his career has been devoted to studying the centrifuge technology and the risks it poses from a proliferation point of view. I'll put up an article that he wrote some years ago, I think called something to the effect that the emperor has no clothes. This is one technology which is very difficult to control and poses a real threat today for even moderately technological states that want to acquire nuclear weapons. We saw before with gaseous diffusion that per stage you had a pitifully small fractionation. It's like 1 part, like realistically 1 or a few parts per thousand. The diffusion, the gas centrifuge is much better than that. It's on the order of, with realistic factors put in, it's still something like about 10%. And that's fantastic compared to gaseous diffusion. The principle, we don't want to go into a lot of unnecessary detail that's unnecessary to do your work, but it is very simple. I think many of you have worked, maybe done an internship in a biology lab or a chemistry lab, and you have test tubes there, and you want to precipitate out something. You put the test tubes in there, and you make this thing spin at very high speeds. And the heavier species, the denser species, will fractionate and go down to the bottom of the test tube. Or if you've been in an amusement park, you can get on this little platform here and stand with your back against the wall. They start this thing spinning, drop the bottom out from underneath you, and you're actually pinned to the wall because the centrifugal force is effectively like is equivalent to it's just like the effect of gravity, which is pinning you against the wall. Now, in gas theory, if you have a force of acceleration, gravity, the gravitational vector here, at a given temperature, which defines a certain energy of the molecules and a certain velocity of the molecules there, there's a criteria relating the gravitational vector and the relative velocity of the molecules there, which determine whether or not you get any appreciable fractionation of the heavier species out. And at the Earth's surface, it's at high temperatures, 300 degrees Kelvin, it's a fairly negligible effect. If I go here and I go up a kilometer, you actually find roughly the same fraction of oxygen and nitrogen. If I cool things down and the molecules are more slow, you will then begin to see the difference, a gradient difference between the two. Here, the same thing pertains. What you do, it's a little bit of a complicated device here, but I feed in the gas here. You see these 3 concentric cylinders or tubes that go in there. I feed gas in. I spin this device at a very high speed, on the order of 60,000 RPM. And so one sets up a tremendous sort of centrifugal force here. And one also sets up a convective cycle. One sets up a thermal cycle here as well. One keeps the bottom hotter than the top. And one finds that in steady state, you actually get the heavier species, the 238 component, which this again is uranium hexafluoride, so it's UF6, atomic number 352, and will preferentially be on the outer radii here, and then slightly preferentially the 235 will be left on the inner part of this. And here's the waste scoop. The heavier thing comes out, and the lighter species here will be taken out, sucked out from the middle, and this little concentric shell there and that will give you the product, what's called the heads, the product, and the waste is called the tails, like that. Okay, the physics was known a long time ago. It wasn't really developed until after the Second World War. It's simple in principle, but it's extremely technological. It really makes technology stand on its head. The forces on the material here, they use a type of steel called barraging steel. We'll talk to Peter Postman, the material scientist here. It's a very high strength steel. You need, today's centrifuges, in fact, are magnetically levitated, and they have to be very, 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 very precisely balanced if you're going to make something, spin at many tens of thousands of RPM like this. So it's something which is very, very technologically sensitive, and for that reason, the technology, components, and so forth, most of the components that go into a centrifuge are under export control. And sure enough, human nature being what it is, over the years, we've actually found some of our closest and strongest allies have not been paying attention and allowed companies to make a profit by exporting this stuff. We actually find German components all over the place where they shouldn't be, but that's the kind of world we live in. Now, this is where things get interesting, and this was, of course, mentioned to you by Professor Knock. A.Q. Khan, who had been working for a company called Urenco, is based in Britain, but operates in Germany, the Netherlands, Britain, and the US. Actually was an expert in several languages. Took these when at that time, Uto called for all his scientists to come back and help him develop a weapons program. He went back and took all of this technology back with him, but then ended up exporting this to lots of countries that are obviously problematic, and we're still dealing with that situation right now. This is what a farm looks like. You've probably seen the iconic photograph of the Iranian centrifuge farm like that. Again, there are many, many, many hundreds of these things in a traditional, kind of a traditional cascade. This was a DOE-supported project, basically a pilot plant. It's still operating, but at a much smaller scale than the original rendition. When it got these large sort of DOE provided loans to actually build up what was a several $100 million plant there.
What's the scale on that?
These things are actually very tall. It actually behooves you to make these things as tall as possible. They typically tend to be on the order of 10 feet or 12 feet high, something like that. I've actually never walked through these. Jake, have you ever walked through
No, but I'm planning on going to Urenco later this semester.
in the Netherlands or where? In
PNNL.
PNNL. Okay. I showed this picture before, a mathematically optimized cascade. I actually, after my last class, went and talked with Phil Kaminsky, formerly the chair of the IEOR department, the executive associate dean at the College of Engineering. He said, yes, this is a venerable problem. He said, what you guys do is actually fairly easy compared to, in biotech today, when you actually have large plants, you have the same kind of thing. You do purification, you do reactions, you recycle, and so forth. So this is a very, very classic operations research problem, the exact mathematical optimization of what a plant looks like. And I'll show in just a second, there are some things which are amusing because they're a little bit, if you don't think deeply about these things, there are some things which defy your intuition a little bit about this, but are in fact very topical and very timely in the proliferation area. And again, how one designs this thing, obviously there are degrees of freedom which are in your control, what you want to optimize, and specifically what fraction that you want out of the back end. If you want weapons grade, it's where you are above 0.9, 90%. At what point, below the feed input here, where you give things which fail the test that go back 1 or 2 stages, give them an opportunity to for 235 to be selected and go up the chain like this. At what point in the enrichment for the the waste product, do you actually then discard this? You start here at 0.72%. Typically, one would then basically give up, and for things below 0.3, 0.4%, you would say, okay, that will go into exit the system into the waste stream. You can get a more efficient part of this optimization. You can obviously get a more efficient, i.e. produce less waste thing by adding more centrifuges back here, but that obviously increases your operating and capital costs as well. As I say, there are some subjective things in what you want to optimize in designing a cascade. Proliferation issues and numbers. The low enriched uranium, LEU, is less than 20%, but typical reactor grade uranium is most of the reactors in the world, like water reactors, are in the few percent range like this. Although the definition of LEU is less than 20% here, let me come back to this point later. If a country makes an argument that they actually want to, or quote unquote, need to enrich uranium up to 20%, you should raise an eyebrow. That's not a typical number for reactors. And for reasons I'll just show you in a second, this should raise alarms right here, because if one has an enrichment program that begins to stockpile things up at 19.5 or 19.8% enrichment, one can legitimately worry that they are contemplating a breakout and a sprint towards the production of a bomb. And you'll actually see the numbers of this in just a second. HEU is above 20, as we mentioned before. Bomb grade stuff is above 90. And as I mentioned here, LEU, if people begin to make the argument that they want to enrich up to 20, you should worry about what they are doing. Okay, now I'm taking a chart here from Ed Morse's excellent book called ALET, The Methods for Non-Proliferation, just appeared a couple of years ago, where he has taken a prototypical optimized cascade. I'm going to show you a chart, and I've blown it up, and because I've blown it up, it's going to show up on 2 pages. So I'll show you this, and then page 2 is this. I've actually 3 pages. I've actually compressed by cutting and pasting onto 2 pages, where he actually has a 42-stage cascade that goes from the feed point, low down here, 0.72%, 0.072, all the way up to bomb grade uranium, very fine bomb grade uranium at 0.94, 94%. And again, it is this teardrop or kind of Christmas tree effective morphology there, where at the input stage, you're dealing with lots and lots and lots. I mean, tons of uranium coming in. Since you're going to purify the uranium, if you purify it at 100%, what's coming out the back end is only going to be 710 to the minus 3 of that. And that is why this thing has this Christmas tree or type shape to an optimized cascade. And here you see in each of these rows, you have kind of the feed enrichment, what comes in. The head enrichment is what passes the test, the 1.1 that or so that comes out. This is the enrichment for what passes the test, which I call for P product. What fails the test at that stage comes out obviously a little bit depleted because there's more over here, there's less over here. It gets sent back. It's like if you fail 3rd grade, you get sent back to 2nd grade. So you can either retry 3rd grade, but mathematically it's better here, since this thing is now at a significantly lower enrichment. What fails is at a significantly lower enrichment. An optimized cascade normally sends it 2 classes back, where this thing would be characteristic of the input feed as before. So there's cascades that are called 1 up, 1 down, 1 up, 2 down, and so forth. Here it shows you the number of cascades you need, a number of centrifuges at that stage, and you see these are quite large numbers. And this thing is called a separated work unit, which is in fact not in units of work, but it's a little bit of an arcane unit which depends on what's called a value function. If you pick a particular cascade design and you say, I want such and such product at the end, and I want such, I will have such and such enrichment that I'm ultimately going to decide to throw out, like 0.3%, and I want to get 0.94 or something like that. That actually is reflective of how many kilowatt hours it will take. That's not kilowatt hours, but it allows you to calculate for a given technology and a given enrichment factor per stage. It is reflective of how much energy it takes to do that. So you see, after I've cut the page arbitrarily from 1 to 21, and then I go to 22 to 42 like that. So it's sort of 21 stages on page 1, 21 stages on page 2. Just by chance, halfway down, you see you've just gotten over here. The head enrichment is slightly over the definition, the breakpoint between low enriched uranium and highly enriched uranium, like that. Notice as the thing goes on, the number of centrifuges goes down, 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 like that. Here we are on page 2. And you see, here you go from the 0.22%, and ultimately is the feed, and ultimately what comes out, the head of the final stage, heads and tails of the final stage, is 0.94%. The total number of centrifuges in all of this is 306, but the number of centrifuges to go from just the breakpoint between low and high enriched uranium to here is only 23. Furthermore, when you count up the separative work units, it's about 154, 158 to go from low enriched all the way up to bomb grade, out of what's a total of 4,400 like that. This is the thing. People say, well, okay, you go from 0.72 to 20%, but from 20% to 100% is a huge gap. Why should I worry that somebody's contemplating a bomb? No. By the time you get to 20%, you're dealing with a much smaller inventory and a much smaller number of separation of the enrichment factors to the nth power to get to bomb grade. By the time somebody has got 20% enriched uranium, the policy people are now calculating in weeks. If they break out and sprint to a bomb, is it 5 weeks? Is it 2 months? But it's like really short. Okay, that's the funny mathematics of this thing. You're very, very, very close to having a bomb once you're at 20%. Jake, you know this stuff very well. You want to make any comment on this? Okay, fine. You studied with Scott at MIT, so you've taken Scott's course. Okay, so that's why I say when you read a lot of literature about what states are doing, and so just now, it was in the paper a couple of days ago, Iran said, well, since the US has backed out of the deal, we are going to go back and we're going to enrich all the way up to 19.8%. So that's where we are. It's a signal, it's a threat, it's a real threat. Okay, laser isotope separation. Another way of the thing which is we could have done to not talk about this. It's a much higher technology affair. The fundamental principle of this, the fact that if I have the same chemical element but two different isotopes, the atomic levels shift and split ever so slightly, actually does give you yet another mass-dependent physics, which allows you, it gives you a handle on which allows you to separate uranium-235 from 238. This was understood shortly after the Second World War, but it wasn't until the invention of the laser that in 1964 was the first demonstration by Theodore Lyman down at Hughes Aircraft in Southern California. And then the invention of tunable dye-pumped lasers, that this actually became a real possibility. So, in fact, when one looks at in detail, spectroscopically, at the transition from the ground state up to a particular excited state here, there is a, sort of like a very small fraction of a nanometer wavelength shift. However, this separation between these lines in 235 and uranium-238 here is much larger than the intrinsic bandwidth of a tunable dye pump laser, and therefore one can selectively excite by putting the laser over here. One can excite some of these lines, excite the atomic state of 235 up to some high atomic state, and you will not do the same excitation in 238. Once this thing is excited, you can hit it with another laser, pop the electron out. Now you've got a charged ion. So you have a charged ion at 235. You have 6, of course, and a neutral atom right here. And then what you want to do is quite obvious. Here's your pump laser. Here's your process laser. You shoot this thing through. Here you have a sort of like a linear oven where you take this, you vaporize uranium. I think they may have actually been using solid uranium here rather than UF6. And here you have two, like a parallel plate capacitor. You shoot the laser through there. You actually get essentially a sort of 3D excitation process by which you promote the 235 to an excited state, and then by 1 or 2 steps, or maybe 2 more steps, you ionize it. Once it's ionized, then of course the uranium 235 ions will come and get collected onto this product collector here. And you run it for a number of hours or days. You take it out there. You basically take what looks like a windshield wiper, or sort of a windshield scraper, and you basically scrape off the uranium, and there you've got your enriched uranium. So that's what it looks like. I was at Livermore. The program began in the early 70s. I joined Livermore in '85, and AVLIS, the Atomic Vapor Laser Isotope Separation Program, was in its heyday. Things were looking great. The leader of the program was Ed Moses, the same guy who later on built NEP. He's a brilliant guy, brilliant project manager, brilliant laser physicist. They built a building with a whole farm of copper vapor lasers. I'll mention interesting context in just a second. And the copper vapor laser pumped the tunable dye laser. The tunable dye laser, they were able to then finally focus on the line of interest for the uranium-235 excitation, so they could for the enrichment. This was then, people always used to joke that LLML stands for lasers, lasers, nothing but lasers. It hasn't been a lasers lab for a long time. Everything that has to do with lasers, whether you're making laser weapons, National Mission Facility, AVLIS, whatever, that was their thing. They actually did successfully produce macroscopic, ton quantities of uranium-235. It was transferred to the U.S. Enrichment Corporation, but then, we decided that the country decided we had more uranium we really needed, and this just was not profitable, and they closed down the program and took a loss, and that was the end of it. This is a high-tech path to enrichment, but not beyond the means of moderately sophisticated countries. I believe that South Africa had a program like this. Lots of countries could do uranium enrichment. It's like in World War II, building an atomic bomb was rocket science. Nowadays, anybody can build an atomic bomb. 20, 30 years ago, you might say only a few countries could do laser enrichment. No, you can get this. A lot of these lasers are just commercially available. The key thing here is that as a proliferation challenge, the power requirements are very low compared to gaseous diffuse centrifuges. A lot of capital investment, you need smart people to do it. It's not trivial. This is going to come up. I mention this because it's going to come up when I talk about the stockpile stewardship program later. Good. What permanent fruit was left behind the lab as a consequence of the copper vapor laser program. You'll never guess, maybe some of you know. Science. That's Claire Max, a friend of mine. She's now a professor at UC Santa Cruz. She's the director of the Lick Observatory, member of the National Academy, premier astronomer. She and Will Happer, a very famous physicist at Princeton, he had been actually the science advisor under Clinton, and then Gore fired him for making suggestions that maybe science we should think about climate change and naturally scientific evidence. So Gore fired him. But anyway, they wrote a paper. Said one of the problems that astronomers have is when they see objects, ground-based things, is you get twinkle, you get atmospheric. You actually get many layers of atmospheric turbulence that limits the resolution you can see things. If you have an object here like a galaxy and another point-like star over there, you can use that point-like star to correct. And now with a classified Air Force program to do the same thing. And Hawaii, there's actually a big glacier there on one of the mountains that they do funky things, right? At some point, the Air Force said, we should really do the astronomy community a favor. Let's let it in on the secret. So in fact, they actually declassified the program. And Claire and Will had actually figured this thing out, and we're on par with what was being done on the dark side. And she's made a great career. All major observatories today have a laser guide star, of which she is the inventor. And I remember when they were testing this every Wednesday night at midnight, if I'd come in for a shift on the accelerator at Livermore, I'd drive over the hill at Castro Valley and go down, and I see 15 miles in distance, there's something that looks like Darth Vader's sword. It's a beautiful sight. You can see this column of light, green light, going up and just disappearing up there. And that was, FAA allowed them for like 4 hours every midnight. There were no planes going around to play with this thing there. And then ultimately it was deployed on Lick, and every major observatory in the world, in fact, big, like the 30-meter telescopes you built, actually almost as a laser light show. They've got multiple of these things designed in. I want to come back to that. That's an important point about the relationship between science and program in the National Lab, because one of my agendas here is that I want many of you to work in the NNSA laboratories. That's my agenda. Many students have come through this course before have ended up working for the federal government, in the intelligence community, the Fort Los Alamos Sandia, and it's all good. So you should think about that. Okay, if there are no questions, I'm going to hop ahead and do a very short piece now. We'll go from chapter 9 to 11. And I want to talk a little bit about testing. Go ahead.
Just, the South Africans had a very purposeful nuclear weapons development program, and one reason they latched on to the laser separation technique is, remember, South Africa was part of the British Commonwealth. They had a number of top scientists and engineers who studied in Britain and also in the United States, and to some degree in Germany. So they were world-class people in this field. And that was the path that they chose, which is a minority selection, but they was, I gather, successful at it until they gave up the whole program.
Turning on my air because I will do one thing here. There we go.
Only some also studied in Australia, which also had outstanding laser physicists.
Okay, in this very brief lecture, I wanted to touch on two things extremely superficially. I'm being purposely superficial on the second one because I'm holding out hope that Kim Leo will be able to join us and talk to us very authoritatively about the Stockholm Stewardship Program. She worked at Livermore for many years, then went and was right here in Oakland as the vice president for the laboratories in UC Office of the President. And after 5 years, she's actually gone back to be the principal associate director for the weapons program at Livermore. I think you could probably put a very safe wager that sometime in the not too distant future, she'll be the director of the lab. She will be an excellent director. She's very knowledgeable. The program she ran before was in non-proliferation, and she'll be able to come and tell us many interesting things. So here I'm going to talk things here where I will I try not to encroach on Michael's territory, which gets into things of history. So people correct me on things. Okay. This is a plot that stops in the year 2010. It shows the US, the Soviet Union, Great Britain, France, China, India, Pakistan, North Korea. And you see here's the first test, the Trinity test. And then you see here 46 was a series of shots. This was Operation Crossroads. And then the Soviets got into the game, and then very shortly both the US and then later, quickly thereafter, the Soviets had thermonuclear weapons. And we were off to the races. The number of shots per year was kind of going up exponentially. 52 was the foundation of Lawrence Livermore National Lab that Teller set up simply to annoy his friends in Los Alamos. And it led to this very interesting dynamic between the two labs. And he set them up to compete against Los Alamos. But both of them end up beginning to do their first tests, then in Nevada. I actually have I should have brought it, I'll show it to you next time. It was a photograph that to this day I think is probably over the desks of most employees of Livermore. It's something I keep as a screensaver just to remind me of the need for humility in life. I forget the name of the shot. The first Livermore shot that happened in Livermore at the Nevada test site, you actually see its 100-foot shot tower, and you see the top of it is slightly crumpled. It was a dud, and I forget the name of the shot, but Los Alamos, of course, then went into high gear trying to put Livermore out of business. There was a turning point because Edward Teller was the one who told the Navy, he said, who wanted a submarine launched ballistic missile system. The first system was called the Polaris. Los Alamos came in and said, well, it's going to be extremely heavy, not such great yield, and it's going to be very expensive. And Livermore said, not so. In fact, delivered the system, which actually was deployable. They actually made a missile, a warhead combination that worked and became the first missile deployed ballistic missile nuclear system. And I think the first, I made a toy model when I was a kid, I think it was George Washington, the SSBN 798. I was born and raised in New London, Connecticut. I actually saw the Nautilus go out to sea on sea trials when I was about yay high on the Thames River. That sort of carbon-14 gauge me. Anyway, here you see a notch. This is the history here is extremely complex, and I think Professor Knocker could tell it better than I do. There was, in fact, a de facto moratorium for a period of about 2 or 3 years. How it came to be, why it didn't last, but then why we actually had a first partial treaty here in 1963, a lot of complex dynamics. The leaders, including military leaders, actually were beginning to get very scared about these things. You had internal dynamics of both the Soviet Union and what's going on in this country. Khrushchev was, in fact, feeling that his hold on power was very tenuous and fragile. He was actually had to put down a party that was, in fact, aiming to unseat him. He himself was conflicted on whether there should be a test ban or not. inside both the US and the Soviet Union, you had high-minded scientists, Tonopah, in fact, being one of them on the Russian side, Soviet side, and people like Oppenheimer and others here, Wolfgang Panofsky and so forth, who's the creator of the SLAC laboratory, who very high-minded said, no, we can do without testing. We're reasonably confident we can detect if somebody tries to cheat. There were other scientists who said nonsense. The lab directors were pressing for the keeping of testing. Military people were almost invariably in favor of continued testing. But the Soviets went on a rip one year and did a lot of testing and then shut off. And they did a sequence of tests. We wanted to do a sequence of tests to test the system, but were frustrated. But Kennedy, I think, then ultimately decided to stick with it once he was elected. At some point, this thing, the Soviets began testing again, and just to show them, we actually went on a rip and started doing a lot of testing ourselves. So it was a very complex history here. This, by the way, is just a summary. Again, this is old. North Korea is now, I think this number is 6 or greater. But the US over the years has done over 1,000, 1,030, the Russians 715. And you can see the rest of the numbers right there. Here, and again, I think these are things that you've heard a little bit before, and I think you may hear Professor Knox lectures a little bit more. Out of this thing of the de facto moratorium that we had at the time, did come out a treaty which limited testing to the underground testing and as well, and that went into effect in 1963. I checked the number; I thought it was 62, but I guess it's 1963. Alternative to say, look, it may be a bridge too far to have a complete treaty banning testing, but if we keep the yield down low, that will, in a certain sense, set limits to the ambition of people who want to test major new systems. That's a partial truth because, in fact, one can make a lot of progress. I mean, a lot of what happens in the testing or development of a new system is not the secondary, it's the primary, the performance of the primary, which is a low yield thing in its place. In itself. So in fact, one can still develop lots of new systems even with a threshold ban in place. We had a de facto cessation here with the US and the Russian Federation. By that time, the Soviet Union ceased to exist to give the Russian Federation. We were doing a lot of testing. When I joined Livermore in 1985, the excitement of the place was palpable. The lights were on, and there were hundreds of people, thousands of people on site at Livermore, 24 hours a day. There were 3 cafeterias, 2 of them served dinner. People were coming and going, the lights were on, people were in the labs because between Los Alamos and Livermore, we were testing about 24 times a year, something like that. It was sort of like 2 a month, boom, 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 like this. And you start preparing your shot 2 to 3 years before, and you're trying to keep the schedule here. I came in the middle of the heyday, I'll talk about it in just a minute, of the Star Wars time. Edward Teller and his minions had actually convinced President Reagan that it was feasible to use a fission weapon to pump sort of medium weight atoms, sort of a linear rod of material of some medium weight, medium Z nuclei, pump the deep shell states up and such that the de-excitation gave you these very, very energetic X-rays, and you would actually get a lasing. You would get sort of a lasing behavior, lasing action, and one could actually project and shoot down Soviet ICBMs thousands of kilometers away shortly after launch. This turned out to be all stuff and nonsense, but it scared the pants off the Soviets. And one can read many theories about what happened to the unraveling and collapse of the Soviet Union. The economics plays a big role in it, and the fact that this crazy thing that we were doing may have contributed to bankrupting. But as cynics say, we bankrupted the Russians, and we came with an eyelash of bankrupting ourselves. The program was enormously expensive. When I was there, Lowell Wood, who was the protege of Teller, had his loyal band of young, brilliant young scientists in what was called O program. They took over their own part of the lab. They had their own series of, in a sense, their own sort of system of classification and access and so forth. And they were coming up with all kinds of crazy schemes there. Peter Hagel's scheme and others. It's a fascinating and somewhat bizarre history. But we were doing these experiments where we'll talk about downhole shots right now, where we were not only, very expensive business of testing a nuclear weapon, but in this shot hole for like 2,000 feet above it, we would have this incredible piece of scientific instrument here, like a gantry with several stages on it, like 100 feet or 200 feet long, with the most sophisticated X-ray optics and other diagnostics. So this piece of instrumentation itself cost $100 million, and of course it gets blown up, within microseconds after the shot. Simply to see, to look at the beam of X-rays that's coming up. And the early tests were promising enough that there was a lot of value made and money came in. And it was a great time. There was an obscene amount of money in the laboratory at the time. I remember one mid-level guy went to Washington, came back late in the fiscal year, advanced to his boss. He said, well, I just brought back another $250 million. He was actually punished. They said, we don't need that money, give it back. So there was a huge amount of money in there to do this strategic defense initiative. This is a complicated business, and I think Professor Knott will talk to you about it. There is, in fact, a comprehensive test ban treaty, but there are 8 countries who have not completed, have not ratified or signed. See if I can remember them. There's U.S., China, Egypt, Iran, North Korea, Israel, India, Pakistan. 8, I think those are the ones. And I think you may be talking a little bit about this later on. But the fact is, since 1992, the U.S. has not tested. The last test, the first test that didn't happen was called Greenwater. I was at Livermore at the time, and the big trailer truck, trailer trucks were on its way down to Nevada. They stopped at a facility called Atlas, and we go further up into the test site. Congress was voting on whether we should basically have a sort of undeclared moratorium. And the lab director, I think the head of the Department of Energy called up the lab called out and said, stop, check into a hotel for the night and wait, don't go any further. And a good friend of mine was one of the senior project managers on that. It was, again, an X-ray, bomb-puff X-ray laser shot. And he was carrying all the sophisticated equipment down there. And a day later, they said, turn around. So they came back. And of course, the physicists like me felt like piranhas on the equipment. And we started taking this thing apart and taking the X-ray optics and the X-ray detectors and the gamma detectors. And that was the end of testing. So Greenwater was the first shot that didn't happen. Purposes of testing. First thing you want to do from time to time, if you are in a mode where you're testing, is just pick a random one off the shelf and say, does it work? Does a particular weapon system, if I pick, we may have 500 of them out there, W81 or something like this, pick one, did it work, did it get the yield that it should? Obviously, new weapons development systems, by the way, stockpile verification is the simplest. But when I tell you a little bit and show you a picture, if I had more time, I would show you more pictures. Even today, it would take years and billions and billions and billions of dollars for us to restore the capability we had down in Nevada to even do a stockpile test. It's a big deal. It's more sophisticated than you think. Testing of new systems, for example, the Strategic Defense Initiative. Weapons effects test. The first shots that we did right after the war, that was called Operation Crossroads. We've seen pictures of it. And what did we want to do? Well, a big question we have is, do nuclear weapons make our surface fleets vulnerable? So the first two shots we did is we did an airburst. We took some old ships, defunct ships from World War II. We just put them out there in Bikini Atoll and dropped a Hiroshima type or Nagasaki type bomb a couple thousand feet above it. What did it do to the ship? Did it snap the hull, et cetera, et cetera? And then we did a shot underneath the water, like several hundred feet underneath a flotilla of ships there, and asked, did the shock wave, what did it do to the ship? So it was testing, effects testing. Training exercise for nuclear warfighting. Well, it's kind of crazy, but I showed you saw a little video on that before. Interestingly, experiments in large-scale civil engineering. Both the US and the Russians did experiments. Edward Teller was a visionary. He said we could recreate the Panama Canal trivially anytime we want. We could even do it better. The Russians themselves did civil engineering. They actually, one of them turned out very badly. There was one shot where they tried to make an artificial lake, and they had a lot of fallout over Japan. It was a very stupid idea. One thing the Soviets did is very good. After the end of the Cold War, I remember several Soviet lab directors came to Livermore and gave a talk. And they said, believe it or not, we actually did use nuclear weapons peacefully. And he said what they said is they actually had a river where they had a huge city that did a lot of chemical processing. They had a chemical industry there. And typical Soviet thing, they would just simply dump the effluent in there, and it was disastrous. I mean, no fish lived. It was brown water. It was poisonous, toxic water. What they did, the Russians did, is they actually went a couple of miles away from the river. They drilled down. They fired off an atomic weapon, nuclear weapon, into hard rock. And we'll talk about this in just a second when we talk about subsidence periods. It forms a glassy cavern, like 100 feet, 200 feet diameter. And when you do it in hard rock, it's perfect and stable and glassy like that. So you make an artificial cavern. What they did is they took the effluent from the chemical factories and they pumped it down into holes. And within a year, the river was lovely. Fish were back, you could swim in it. It was beautiful because they weren't propping up the river anymore. And at some point it filled up and they did another one and another one. After the end of the Cold War, when nobody tested, they ended up throwing the effluent back in the river. And he said, and then the Soviet lab directors were the Russian at that time, the Russian lab directors were actually very sad about this. Political messaging, in fact, I think probably every nuclear weapons test is in one way or another a political message, and maybe I've forgotten some modes why we test. If you fly from Oakland, if you ever go down to, as we do quite often, if you ever fly down to Albuquerque, go to either San Diego or Los Alamos, in the old days, the flights were kind of redirected, were not allowed to go there. Nowadays, they don't particularly care. Often, your flight route will go right over the Nevada test site. The Nevada test, 95% of Nevada is federal territory. In the southwest corner, you have you have what's called the Tonopah test range, where the Air Force does a lot of funky stuff. A little bit further away, you have Groom Lake and Area 51. It's real. But this, where they do stealth testing and lots of other things that we don't know about. But the Nevada test site inside of Tonopah is the size of Rhode Island. It is an absolutely immense place. When you fly over there and you look down, has anybody flown over there?
I've been there.
Yeah. The thing that's amazing, when you look down, you say, my God, it looks like a golf ball. That's what it looks like. Those are not surface tests, those are underground tests. And I'll show you this in just a second. Jackass Flats, Frenchman Flats, there's several areas there where they would do these shots. And over the course of the years, hundreds of square miles are pockmarked with these large craters, which are sometimes a few hundred feet across and maybe like 100 feet deep. The Sedan crater, which was again an attempt at civil construction, is about 700 or 800 feet across. It was a near surface, deliberately a near surface event, and it's the largest man-made crater in the world. It's actually a point where tourists can go up and stand up at the edge of this thing right here. And as you saw in the previous lecture, surprisingly, this thing is only 65 miles northwest of Las Vegas. And, one of the things that the Las Vegas is always worrying about is, how far should we allow the city to expand if and when, who knows, we get back into a testing regime. We'll look at the subsidence crater formation in just a second. Quiz question, how many different states has the US tested in? This is kind of interesting. 3. Or, okay.
Yeah, I think 3.
It's 5, actually. Obviously, New Mexico.
Were 3 of them the ones I was thinking of?
Well, we'll find out. Obviously, the 2 obvious ones are we mentioned New Mexico and Nevada. Where's the next one?
Arizona.
No, Mississippi. We actually did a civil construction test there. Alaska. The largest underground test that Shanika shot was 5 megatons, was done in the Aleutian Islands on Sitka, way up there. And for whatever reason, I don't know why we did one in Colorado. Nice environmental state, so like that. Anyway, it's a nice trivia question. Let's show you, why do you get a subsidence crater? Let's show that. Give me some sound here. That's interesting. Why is this happening?
I think you need to drag it up.
I need to drag what?
Drag the window over to the other.
Oh, but wasn't I mirroring?
No.
Okay. How do I drag it? Oh. It's always good to get smart. I mean, it was obviously we've been mirroring before.
It's not letting me drag it.
Okay. Is it up, down?
3, 2, 1. I think you may have hit one of the hot corners.
What's on this thing?
So your top
Move
bar,
to the
the
front
bar
corner.
is gray, so I think you hit a hot corner that got rid of all the pages.
Come here. All right. You're clearly next right here.
I
Okay.
don't know, this is just a test.
Okay.
Why don't we open up the displays menu?
Oh, all right. There you have it. All right. Let's back up here. And thank you. As you notice, there's a lot of stuff for nuclear bomb junkies on YouTube. There's all kinds of stuff.
10, 9, 8, 7, 6, 5, 4, 3, 2,
Only watch 2 or 3 of these.
0, 9.
You'll see, we'll do 2 or 3 and then I'll explain what you're seeing.
7, 6, 5, 4, 3, 2, 1, 0.
Notice the shock wave hit, you saw a little bit of dust come up from the ground. The shot is 2,000 feet underground, approximately.
10 seconds to collapse.
And you can see more and more of these. So let me show you what your
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. 0 time. 10 seconds to collapse.
Okay. So what you're looking at is the following. I mentioned that, get the lights on again. So a standard test, underground nuclear test, you have, typically, this is classic thing, when our reconnaissance goes over, our satellites go over, and you see somebody drilling a hole, and you see a bunch of trailers with cables running in towards the hole. Get a clue. That's what's going on. So you've got this hole, which is typically, for a typical test, is not very big. It's about maybe 30 inches, about a yard in diameter. And you put the device down here with these cables. This is about 2,000 feet. You will put diagnostics of various sorts above and below the device, like this, trailers. When the bomb goes, oh, by the way, then you backfill it with concrete. Don't forget that. That's very important. Even when you backfill as well as you can, you almost inevitably get some effluent, some gas, radon and other gases, xenon gases, which are indicative that testing is going on. You'll see particulate matter. And this is how we actually monitor what other countries are doing. We have airplanes that will fly around in the Northwest Pacific and so forth. No matter how carefully you try to do this, there's always some leakage up through the Earth. And therefore, these are forensic signatures that we check for. After the bomb goes off, you get basically, you mentioned before, a glass, I'm writing scale, you get basically a glassified sphere, depending on the magnitude of the shot, that may be 100 feet in diameter. If it's hard rock, it'll be stable like this. It looks like one of these, what are they called? Things like you sit on coffee tables with crystals on it. It's sort of like a cyst or something like that. And what happens here in the stratigraphy here is that this thing will begin to collapse. So this thing will collapse, and then when the guy said they can actually predict when this is going to happen, the volume that is restored by the collapse of the vacuole here ends up being a depression up here. That's what you're seeing. The stuff that you see, when this happens, of course, a lot of dust gets thrown up in the air, but it's nothing more than the formation of that, what's called a subsidence crater. Maybe more details than you want to know. Okay, let's at least get stockpile stewardship done in at least a superficial way. 1992 happens. People talk about the peace dividend. Kumbaya. We have no more Cold War with Russians, billions and billions and billions of dollars. In fact, we shouldn't need to, in terms of our, the maintenance of the U.S. stockpile, all our surveillance things that we can lighten up on, and we can redirect this towards social programs or other good and wholesome things. Well. Be careful. So I think there's always been very strong bipartisan support that we do need to keep up a strategic deterrent. And even though we've been worrying in recent years about the Chinese, I've known Professor Knox for a long time, and I always remember Professor Knox saying, don't forget the Russians. He's been saying this ever since 1992. And he was right, because the Russians are again, they're problematic, the Chinese are problematic, we have other countries that are problematic. So we've always had strong bipartisan support for a strong strategic defense, a triad, that we've talked about before. Now we are in a very, very different situation than no one had thought about. In the days of testing, we would develop a system, and the expected lifetime of that system was, the number I keep in my head is about 12 years. In other words, yes, it should be engineered very carefully and thoughtfully and robustly, but in fact, you did not need to think about lifetime issues, because what the heck, we're going to have a better system in 12 years. We just kept going up and up and up. Now we're in a situation after 1992 where we say we want to keep a robust nuclear stockpile, but there's going to be no more testing. It's not been of the mind that they want us to develop very new types of designs. So you're kind of stuck with the actual physical bombs that you've got with some component replacement for 10 years, 20 years, 40 years, 60 years. They're going to be around for a long time. This guy here, Vic Reese, is a brilliant guy. I mean, he's one of the most creative and brilliant thinkers this government has ever had. He's done lots and lots and lots of things in his government service. He was the Assistant Secretary for Defense Programs in DOE. He was Deputy of OSTP. You know him before than I do. He's had lots and lots and lots of wonderful contributions to this country, national security. He conceived of the idea to say, look, we need a program that allows us to have confidence in the stockpile, even when these things are way beyond what we ever dreamt their shelf life needed to be. He came up with the idea in conjunction with the 3 lab directors, and I heard that Bruce Carter at Livermore was probably, of the 3, the one that I think was his real compatriot in this. The Science-Based Stockpile Stewardship Program, not called Stockpile Stewardship Program. It would be fundamentally a computational program underpinned by experimental data. In other words, the dream, the end goal, was ultimately computers that would be sophisticated enough that would not only understand the microphysics of each aspect of a nuclear weapon, the chemical high explosive, the primary, the radiation flow, the secondary, this, that, but in the fullness of time, we would actually have an integral computational model of the highest fidelity, underpinned by piecewise experiments in material science, hydrodynamics, in the laser atomic physics world, what are known as opacities, the absorption of X-rays as a function of energy for these very complex atomic spectra, thermodynamics, everything like that. As an experimentalist, I kind of get nervous because we always say science is primarily experimental and secondarily theoretical and computational. This thing was computational underpinned by experimental data, but it is what it is. The way you formulate the problem to Congress and to the public is to say the following. Imagine that you have a car in your garage, and you are not allowed to drive it except under one condition. If your child or spouse is all of a sudden critically ill and you have to make an emergency trip to the hospital, you have to turn it on and it must work. You don't know when that time is going to come, but it might be 7 years from now, it might be 21 years from now, it might be 30 years from now. You are not allowed to drive the car until you go in there, and at that critical night, unexpectedly, you realize you have to go to the hospital, you have to turn the key, the car has to work. That's stockpile stewardship. So we have the nuclear stockpile that was designed for about a 12-year shelf life. It is now going to be sitting there for years and years and years and years. Yes, Congress will allow you to do the routine replacement of components. And by the way, these are sophisticated things. You know how many components are in a typical nuclear weapon? Counting all the electronic widgets and this and that. It's about 6,000. They're very complicated. And you don't routinely go in and do a substitute, say, well, 20 years ago, there's this little foam cushion here. We got something better here. You don't. likely change something even of what you thought would be a trivial nature, because it may have different properties and may have different aging properties. Anyway, so the idea was to do science of all different types, and then to create this large sort of computer computational architecture there. And what wonder of wonders, this is a coincidence, the budget of the labs required to do this program, oh, by the way, just happened to be the budget they were getting back to doing testing, and employed exactly the same number of people. Congress loved it. It actually was not a problem selling it, and it's defended, and this has gone on. They organized this thing to show that we were, executing the program in a project-like way by which we organize these things in campaigns, campaign 1, campaign 2, campaign 4. One of them is sort of, primary physics, radiation physics, whatever. And you're actually able to draw graphs and explain to policy people and congressional staffers that we're making progress. We had milestones and we're meeting those milestones. It has driven and continues to drive phenomenal science. And interestingly, one of the fruits that came out of the Stockwell program, back in the 80s and 90s, we were getting sort of kicked around by the Japanese and high-end computing. The Japanese had taken the lead. The NNS, what became later the NNSA, the semi-autonomous part of DOE, got stood up in the year 2000. All of a sudden, part of Vic Reese's vision was a spiral development. Livermore, Los Alamos, Sandia, Livermore, Los Alamos, Sandia. Every 2 or 3 years, you get another factor 3 speed up. We were the first to break through the petawatt. And now, even though the Chinese have been getting into this business, the US computational program, we now have, I think, number 1 and number 2. Actually, the fastest computer in the world now is in Oak Ridge. It's 250 petaflops. That's incredible. That's a factor of a couple hundred more than when I joined the lab. The one at Livermore called Sierra is 125 petaflops, and they do these. You can actually do high fidelity simulations of materials, shocked plutonium or something like that, with literally hundreds of billions of atoms in the computational space. It's really fantastic what these guys are doing. Part of his genius, he said, every lab needs an anchor facility. He said every lab needs its Nordstrom's. You've heard him say that. It's his famous mantra. And at Livermore, we've done quite well. We actually built the NIF, the National Ignition Facility, which allows us to test lots of stuff, both basic physics and simulations of what goes on in nuclear weapons, principally aimed at the secondary weapon. Los Alamos, the dream they want to do is build something called Marie. They're not quite there yet. They've been at it for a while. They've got this 800 MeV high current LINAC. They actually want to build kind of a sort of a 3-electron laser driven, such that they can shock material and probe it at the same time. That would be a $2 or $3 billion thing. Sandia got an upgrade to their Z machine, which is a pulse power machine, which also allows you to create instantaneously very high density, many hundreds of eV or higher temperature systems and probe them, which are stimulants to the weapons. Los Alamos has this thing called DART, Dual Axis Hydrodynamic Radiographic Testing Facility. We talked before about hydrodynamics. They take surrogates of plutonium primaries, and again they set off. They just set the thing up. They crush it. It all comes together, and then in the last milliseconds, they actually have these 2 orthogonal flash X-ray machines, but they're not like your dentist, which operates at 20 kilovolt X-rays. This is like 3 MeV or 6 MeV. They're very, very, very high energy X-rays because this is it's a very dense, high Z material. You get through that stuff and make the radiograph takes MeV, not KeV, and you can actually get multiple images, microsecond by microsecond, of this thing as it comes in, and you see all the gnarly stuff that's going on, and maybe good or maybe bad, as you crush this thing. So that's basically it. I think. What else did I want to say about this thing? You should have guessed. It's not simply about the lab and keeping the capabilities together. What's most important? I mean, you got to remember, the last lab director at Livermore who had actually any underground test experience was George Miller. were now several directors after that. 50 years from now, you'll have people who were not even born as the lab director back when we did testing. How are you going to have a workforce that knows about this stuff? And how do you attract not people who are going to do Rust Belt stewardship, but high quality thing, and makes it an exciting place for young people like you to go to? You need a place that does high science. And that's what these labs are doing. They're exciting places with a great mission. And part of the Stockholm Stewardship Program is keeping bright people from Berkeley and MIT and Harvard and Stanford and so forth going in there every year. I was recruited there, believe it or not, to start a High-Energy Physics program. I actually built up, a High-Energy Physics program where we started interfacing with SLAC and Fermilab and CERN, and we started being partners in building accelerators and detectors that were, hundreds of millions of dollars. We had a great scientific role. I recruited in lots of smart people from high-energy physics who ended up having nice careers in doing national security type stuff, and they love it. That's the other subtext for why we have a Stockholm Stewardship Program. I may have forgotten something. Why don't you have a few comments here about Stockholm Stewardship Program? Kim will tell us more if she can come. But
Yeah. No, I mean, I think it's been a great success, and Vic Weiss is still around. He was at DOE even recently. I think he's sort of semi-retired now.
he went on a thing about nuclear power, so I mean, he applies his energies in his brain in many areas.
Yeah.
Okay.
So I think there's the question whether under Trump, there would be renewed interest to start testing. But so far, no evidence of that, but gossip about it.
Let's hope we keep away from that.
Yeah.
The next time I talk, I will talk about radiation effects and sort of nuclear weapons effects. But that's okay for now. I think we got through everything we needed to do at this point. Any questions?
More of an announcement. Raymond Jama, who we've talked about before, recommended a lecture that's in 30 minutes in the Lighthouse Chevron Auditorium by Admiral James Stavridis. And apparently that should be pretty.
That's why we're dressed up today.
Oh.
So, yes.
It's called The Voyage of Character. This is a fella who was the admiral in charge of the NATO European forces.
Yep.
The guy who's giving the talk, and he has a PhD in his own books and articles, so he combines academic and military policy. It seems like Marvel.
He was the dean of the Fletcher School at
Fletcher
Tufts
School, yeah.
until recently. This is the annual thing. It's called the Nimitz Lecture.
Yeah.
Admiral Nimitz was, in fact, started. Berkeley was one of the first 6 naval ROTC units that started in 1926. He was a lieutenant commander at the time. Then, of course, he became the guy that led the naval victory in the Pacific Theater. It's the last 5-star admiral we've had in wartime. And he's just an incredible person. You should read his biography. Came from a German family in Texas, but he and his wife loved Berkeley so much they made their home there. I know where their house is on 785 Santa Barbara Avenue, just north of campus. Man, it's good. So,
Stavridis is outstanding. We've all enjoyed him.
thank you for announcing that. Great.
And next will be the project discussions by you guys.
Yep. So be sure to keep that in mind. You're supposed to meet with your groups and prepare about a 5-minute presentation if you're in groups 1 through 5.
Terrific.
I have fun doing this.